Well, we're back at the physics video lecture. Welcome. This is Psci 168 video lecture 28. Okay, so today we're going to do the theory of the heat engine. I showed you guys some demonstrations the other day. And this one is going to be very theoretical. I'll start out with a picture of what we saw though, and then we'll take it from there. It probably won't run that long, but I'll include a couple little assignments. So here we go. We're doing heat engines, and now that we've seen them, we can kind of review it quickly and remind ourselves what was going on there. We always start from the mechanical equivalent of heat. That's something we learned, that a calorie, 4,186 joules, we would like to just burn fuel and get useful work out of it. And when I generalize this whole concept, we'll see we don't necessarily have to burn fuel, but that's where we start with. So we're burning fuel to obtain useful work. So that's the first thing, useful work, from thermal energy into useful work. Good, so I always start with the mechanical equivalent of heat. The example that we'll concentrate on this time was the steam engine, the little steam engine I showed you. Here I'll do some colors. So we'll have the fire. So we've got fuel producing our fire. So that's the actual source of the thermal energy. The mechanism is this boiler. Ours has a little window in the end that shows us that there's water inside, and we get a bunch of steam, which we pipe on over to a cylinder with a piston inside. Okay, and this piston here is connected with a connecting rod to a flywheel. So if we can get the steam to push the piston forward here, it'll actually turn the wheel. And in the process of being pushed forward, work is being done. Okay. So that work, I could even write here, we've got that work, force times displacement. So we know we're getting that. On the other hand, to complete a revolution of that wheel, to complete one revolution, we're going to have to open a valve every one revolution, or every half revolution. We're going to have to open the valve to let that steam be ejected. And because of that, and we had this in our other example as well, we're operating between a high temperature, here, let's use another color here. We're operating between a higher temperature and a lower temperature. That's very crucial to the heat engine, higher temperature and a lower temperature. Good, so that's what we talked about last time, and yeah, this is a steam engine. You know, I encourage you guys to get some nice printouts and some interesting pictures of these things. Good. So now we're going to turn this into a schematic of the process. Very stereotypical drawing that you'll find all over the place if you look this kind of thing up. So the next process, or the next topic, is the schematic diagram of the process. So this is what it all comes down to. We have, I'm just going to draw these boxes here and arrows, and then I'll discuss them. So here's our universal heat engine schematic, and here's the way we understand it. We have here what's referred to as a high temperature reservoir of thermal energy. So that's the high temperature reservoir. temperature reservoir, E of thermal energy, so it's a high temperature TH. And what it does, what we do is deliver a quantum of energy at high temperature to the engine. So this circle here just represents the engine. So it receives some energy, this is in joules. And what does it do? It's kind of like here, it receives some energy, that heated steam, and it does some work. Okay, so this arrow represents the work that the engine does. And if we could just have this cycle, in other words, energy turning into work, it'd be nice, but it's not possible. We've seen in our examples we have to let out that exhaust, and that's represented here. Thermal energy at a lower temperature is then released to the low temperature reservoir. In our example up there, the low temperature reservoir is just the ambient atmosphere. So this is the low temperature reservoir. And this is QH, that's thermal energy from the high temperature reservoir, and ditto here, thermal energy at the, being delivered to the low temperature reservoir at that lower temperature. Okay, so that C refers to T sub C, that H refers to T sub H. So that's the process, and it's supposed to be cyclic in that it repeats itself. So you get the QH, does some work, you get the exhaust here, and you could say that was one cycle, and then it repeats itself, okay? So that's the schematic of the process. And what do we have here? We have two temperatures. Temperature is going to be in Kelvin. T in Kelvin. We'll see in a moment why we have to do that. And the thermal energy in joules. Work in joules, thermal energy, low temperature in Kelvin. So that's the idea, schematic of the process. We just have temperature, two different temperatures, energy, one form, and work right here. So far, so good. Now, and that's supposed to represent all heat engines at some level. Okay, all heat engines can be represented in this form here. Okay, so what's next? The question coming back to here is, there's a certain amount of work we want to get out, namely as much as possible. So the question that's going to be asked right here in our fourth point is, how much work can we get out? In other words, what percentage of these 4186 joules can we get? Obviously not all of it, because we had some heat coming out the tailpipe, right out the exhaust, and so that's subtracted from the work there. So let's call this topic here efficiency. How much work can we obtain? The more the better, right? It's like with an automobile, how many miles per gallon? Okay? The more the better. Okay. So I'll define the efficiency, letter E. Yeah, this is very logical. It's just the amount of work that you obtain divided by the amount of thermal energy that you put in. So that's a ratio. And it's clear, and I'll make that explicit as well, that this number is less than or equal to 1. Okay. Why can you not get more work than you put in as thermal energy? because of energy conservation, right? That's impossible. So, important note, E is just a principle less than or equal to 1 because of energy conservation. Right? We're not creating any extra energy, we're just changing its form from, thermal energy to work. So far we realize that the efficiency is definitely less than or equal to 1, and when we think about some of this energy going out to the atmosphere, it's in fact going to be strictly less than 1, but on principle I'll just leave the equal there as well. Good. So far, so good. Next, I'm going to do an analysis of the ideal engine, okay, and see if we can say more about the efficiency than just this. And in fact, we can. So to continue this analysis, we'll talk about the ideal engine. And the ideal engine has no losses. So if I have this diagram, remember I said this is all the quantities we're going to talk about. So there's no extra loss due to friction. There's no extra loss due to heat going anywhere else except the exhaust. So if I say an ideal engine, it's no friction, no other losses. For example, a real engine, the engine gets hot, the engine gets warm, you put your hand on the hood of the car, it's warm. Okay, that kind of loss is being shut out here. We're saying the only heat that leaves this thing is out the exhaust pipe. And there's no friction. Okay, so that's going to be the ideal engine, and we can analyze the ideal engine. Right, and then the result of the analysis will be the upper limit for efficiency. So that's really important. So here we go. We know friction, no other losses. And we now can just write energy conservation down. So QH is the energy in, going to be work plus QC, the energy out. Okay. So this is conservation of energy. Then we can take our efficiency definition. So now this is the general definition. Now I'm going to have the ideal efficiency. I don't have to write these names here, but I'm saying it. So the ideal efficiency is when I do the QH or the W divided by the QH. So let's substitute the W in. The W is QH minus QC. Subtract the QC to the other side of the equation. So it's QH minus QC divided by QH. And a little bit of arithmetic tells us that that can be expressed as QH over QH is 1 minus QC over QH. So now I have an expression for the ideal, or the efficiency of an ideal engine, and we can see it literally is 1 minus something, and that part that we subtract off depends on the ratio of QC over QH. For example, if half of the energy turned into work and the other half turned into exhaust, then you would have 1 minus 1/2, which would be equal to 1/2. We'll actually see later that an efficiency of 1/2 is actually very good in heat engines. Okay, so very good in fact. Okay, now we have made that explicit. Okay, that's more than just this general one. This is just the definition, and this is its application. Now, there's one more thing we can do, and this is what we've been building up to here. So we're going to continue the analysis. We're going to call this the entropy analysis. This is actually the reason I brought entropy into the discussion the other day. Entropy was a pretty technical thing. We didn't really need it, except we want to talk about efficiency of engines, and you'll see it comes into play in a really interesting way. So I'm just going to refer back to our chapter on entropy, okay? And what we're going to do is analyze the entropy change of a cycle, okay, of this ideal engine. So delta S total, remember we had this delta S was equal to Q divided by T, and the temperature was in Kelvin. So for our engine, delta S total is delta S, I'm just going to say, of the H part. All right, delta S of H plus delta S of the work part of the engine plus delta S of the third process here. Now, delta S of H, that is Q sub H divided by T sub H, and because the energy is leaving the reservoir, it gets a minus sign, okay? So my Q's are going to be absolute values, so that gets the minus sign. Now this one is interesting. The entropy change of the engine is 0. And that's because it's an ideal engine and it's a cyclic process. So the idea is this engine, makes one complete turn, let's just say, and it's exactly the same as it was, before, which means that there's no increase in disorder. It's the same engine, it hasn't worn out a bit, it's completely ideal, okay? So that's why I get to put a 0 here, and then delta S sub C here is the plus Q sub C divided by T sub C. So that's the entropy analysis. And you guys remember, this just depended on energy flowing from hot to cold. It was that fundamental. But what we had seen was energy flowing from hot to cold means that this is always greater than or equal to 0. So what I've done right here is my second law of thermodynamics. Second law, couple exclamation points there. So all that remains for me to do is to draw some conclusions out of this inequality. So completed. So delta S total equal to this expression here, greater than or equal to 0. Okay, I'm going to leave my picture up and erase this definition now that we've used it. So 6, we'll do 7 right here. So now my 7th point. I've got this E ideal. Okay, let's go here first. So I have, from this equation here, we now have QC over TC is greater than or equal to QH over TH. Okay, so I've drawn the conclusion for there, or I can write QC over QH is greater than or equal to TC divided by TH. So I've just, and this one we're going to use, right, I've just rearrange this expression, this inequality. But what I'm going to do now is plug this into here. In fact, let's name this star, and we'll name this here double star. Okay. So I plug double star into star. I'll even call this point 8. Take double star into equation star. And see, I have a greater than or equal to QC over QH greater than or equal to TC over TH. So 1 minus QC over QH is less than or equal to 1 minus TC over TH. So the combination of these two equations tells me that E ideal is less than or equal to 1 minus TC divided by TH. And yeah, that's the grand result I wanted to show you guys. I have to convince you how important it is. Okay. So the efficiency of an engine, and there's our engine here, depends on what? The ratio of the operating temperatures. Apparently, the larger you make this denominator here, the smaller this part that you're taking away from the 1. Okay. But it's also kind of amazing that just based on the law, second law of thermodynamics, based on the fact that energy flows from hot to cold, that we can make this kind of a statement about the efficiency of a heat engine. And this is, this is the absolute limit in efficiency. It simply depends on these operating temperatures. So I will define now 9.9 here, what's called the Carnot efficiency. That's it. Wait a minute. So it's C-A-R-N-O-T. Carnot efficiency, that's the French engineer who figured this out for the first time. And that is defined as just this expression here with the equal sign. So E sub C is equal to 1 minus T cold divided by TH. That's the Carnot efficiency. And here, get this. We will do a couple of examples now. And I should put a couple of words here. This is the maximum conceivable theoretical efficiency of a heat engine. Something that turns random thermal motion, thermal energy into useful work. So I'm going to erase all of this now. So yeah, this is a really theoretical section, but we've done everything. We've talked about all of this, so I couldn't resist in presenting it to you. So I'll give a couple of examples, and I will have you guys work a couple of examples. Pretty much everything, I will summarize the formulas again. In fact, let's summarize these now. So first of all, a note, maximum theoretical efficiency. And based on energy flowing from hot to cold. So this is very rigorous. Okay. Based on this cartoon of ours, right? TH Q flowing to TC. Okay, I'm going to summarize these expressions now. So 10. So for our heat engine, we have a few relations. I just want to put them all together. We have efficiency in general is work obtained over thermal energy put in. We have, for the ideal engine, QH is W plus QC. Okay. And so this was the energy in, and this is what's sometimes referred to as the waste heat. If you're reading about this, that's the kind of terminology you'll run across. And then we have the Carnot efficiency. So once you've been through this, and you remember our picture there, you just have a pretty compact set of equations to work with. This is the definition of efficiency, this is conservation of energy, and this is based on second law of thermodynamics, entropy increases. So I'm going to leave us with a couple of examples. The first one is if we have an energy that runs between boiling temperature and room temperature. Okay, so let's say TH is 100 degrees Celsius and TC is equal to 20 degrees Celsius. Okay, boiling and room temperature. The first thing you have to do is convert both of these to Kelvin. Okay. So, because, did I say it? I mentioned it once, but I'm definitely mentioning it now. You're not allowed to use these Celsius temperatures in this formula. So we have to convert to Kelvin, and this would be 373, and this would be 293 Kelvin. Then you could find out the Carnot efficiency of such an engine would be 1 minus 293 divided by 373 equals homework. So make sure you take out your calculator and figure this out. I'll tell you right now, it's approximately 20%. You want to get the exact number. Approximately 0.2 equals 20%. A little bit more. So make sure you calculate this one. So that would be an example. And as a problem, this is the kind of thing we could put on the exam later. So here's a problem, and I'll let you guys finish it. Here's the idea. Suppose we can operate between room temperature, which we now know is 293. So for an engine, and an ideal engine, sometimes they refer to it as a Carnot engine, but right now in these problems, I'm referring to this thing here. So for an engine that operates at TC equals 20 degrees Celsius with 50% efficiency, what we want to do is find the high temperature. 50% efficiency, comma, find TH. And you find TH first in Kelvin, and then you can convert it to Celsius. In Kelvin and in degrees Celsius. Okay, so for an engine that operates with TC equals 20 degrees Celsius, which we know is 293, and it's operating at 50% efficiency, find TH. Well, what we're saying is we're solving this equation. We've got to do a little algebra where E sub c is equal to 0.5. So note, what we're looking at is E sub c is equal to 0.5, so we would be solving 0.5 is equal to 1 minus 293 divided by t sub h. So you'd have to do a couple steps of algebra, arithmetic, whatever you want to call it. Solve for t sub h. Your answer will be in Kelvin first, and then you subtract off 273, then you can get it in degrees Celsius. So good, let's call that a homework problem as well. And I should point out, I think I mentioned earlier, this 0.5 is a very good value for a heat engine. You know, we have gigantic power plants that run, say, on coal or natural gas or oil, and their output will be thousands, say 1,000 megawatts, which would be 10 to the 9 watts, so enormous output, and 50% is a very good number, maybe even better than what's even possible. Say 45% is good. So let's say 50% is good. Then you have 1,000 megawatts driving your civilization here, but you're giving off 1,000 megawatts of heat. It has to be cooled somehow. They will use rivers. They'll use river water sometimes to cool off this machine, to get rid of all that waste heat. So on a large scale, you can see these are really important quantities, but they're true on any scale. Okay? It's difficult to actually get the temperatures to be this low because it means you have to draw all the heat off without it heat soaking the engine. You know, if you can't draw the heat off efficiently enough, it moves up, so to speak, into the engine and reduces the efficiency. One way to look at it. Okay, this was a technical discussion. We have these two numerical problems. We consult the clock. I'm not going to do much more today than that. Yeah, that's a good, that's all I want to tell you guys today. But this is really important to study because I'll continue referring to it. Having done this, you know, talked about the heat engines, the schematic, we're going to go back to some other, let's say, somewhat exotic type of heat engines, technologies, as well as processes in nature that can be interpreted as a heat engine. Okay, so there's a lot of interesting stuff in the heat engine, but for the moment we were talking about cars, steam engines, power plants. I had told you guys to look up images and print them out, and we'll return to that topic next time. I can give you some ideas, some pointers on what will be good to print out for your notebook. Good. See you guys next time.